Welcome back, everybody. This video is all about trigonometric equations. Earlier, we studied this idea of a trigonometric identity, and those are statements that are true no matter what x you use, as long as it's in the domain of our functions that we're worried about. Well, trigonometric equations are going to be true for certain x values. Sometimes it might be an infinite number of x values, right? And there may be a pattern in the x values that we have, all right? But it's definitely not going to be all of our x values or theta values or whatever our variable is. So the motivation behind this is whenever you do some sort of a trigonometric modeling problem, all right, like for example, in this case, this is giving the height of a tidal situation. So we've got our height in meters of our tide, and then we've got our time in solar hours. And so maybe what we want to do is we want to figure out when the height of the tide is 0 meters, like at baseline, basically. Or maybe when the height is at 0.5 meters. And so in these cases, we're actually able to set our equation equal to whatever value we want and solve for certain values where it's true. And we can find out what time we're going to be at a certain height with our tide, all right, or any other situation that involves trigonometric equations. So a trigonometric equation is just an equation that's true for certain values of a variable, but not for others, unlike an identity. We've got a few examples and some tricks, just like we did with identities, try to solve these trig equations. So let's get going. Example number 1, solve 4 cosine of x minus 2 equal to 0 for what we call general solutions, and then also for solutions on the interval 0 to 2 pi. So the first step, generally when you're trying to solve these trig equations, is to isolate the trig expression. And what does that mean? Well, we want to get the cosine of x by itself. So what we do first is we add 2 to both sides of the equation, and we get 4 cosine of x is equal to 2. And then we want to divide by 4. And so now the cosine of x is by itself, and we get cosine of x is equal to 1/2. Then in order to find our solutions on the interval 0 to 2 pi, all right, we need to try to find where cosine is equal to 1/2. Well, in the unit circle, cosine is the x coordinate, and we can see right here that it happens at pi over 3, and then it also happens down here at 5 pi over 3. All right, so we get those two solutions that occur on the interval 0 to 2 pi. Notice, by the way, that this statement is different than the statement of finding the inverse cosine of 1/2. All right, inverse cosine is just like when we already have a square root and we say, well, x is equal to the square root of 5. Well, we've already kind of solved for it. We already know where we want our answer to be. All right, in this case, just like if we had a statement like x squared is equal to 5, all right, when we try to solve that equation, we're going to get multiple solutions. Well, in this case, we get multiple solutions because there are multiple x values that actually give us the statement cosine of x is equal to 1/2, right? It's the idea that inverse cosine actually wants us to have a function, right? We want one output for that, but this is solving an equation. It's an equation that could be true for many values. So in this case, we get x is equal to pi over 3 and 5 pi over 3. So to write a general solution, this may look familiar. What we do is we say, well, we're going to get a solution of pi over 3, but if we were to go around the circle another 2 pi times, we would actually get another solution. In fact, we would get the number 7 pi over 3, all right, if we added 2 pi to this. All right, so, and we could keep on going and add another 2 pi or subtract another 2 pi, and we get a whole new set of solutions. So where we say k is an integer, we say that our solutions are pi over 3 plus 2 pi k. And then it's the same for 5 pi over 3. If we went around the circle another time, all right, we would get another solution. And if we continue to go around the circle, we continue to get solutions. So we would say our second set of solutions is 5 pi over 3 plus 2 pi k. All right, example number 2, solve cosecant squared of theta is equal to 4. So you notice that we've got a squared function in here. So anytime we see something that's not sine, cosine, or tangent, it's usually helpful to try to write it in terms of our reciprocal properties. All right, and so what would that mean? Well, it means that since cosecant squared of theta is the same as 1 over sine squared of theta, that means sine squared of theta is equal to 1/4 in this situation. So step 2, don't forget the plus or minus when you take the square root. So in this case, we get sine of theta is equal to plus or minus 1/2. And then now if we want to find our solutions on our unit circle, we would notice that we get where sine is equal to 1/2 or negative 1/2. That's where your y coordinate is either plus or minus 1/2, and that's at pi over 6, 5 pi over 6, and 7 pi over 6, and 11 pi over 6. So all those values would give us a solution on the interval 0 to 2 pi. Now, if you're going to write your general solutions, all right, all you have to do is add 2 pi k to each one of those solutions that we have. So we would get pi over 6 plus 2 pi k, 5 pi over 6 plus 2 pi k, 7 pi over 6 plus 2 pi k, and 11 pi over 6 plus 2 pi k. Now, if you notice, there's a lot of patterns to some of these solutions, and you don't have to write it necessarily in this form, although this is like the most simplistic form that you could write these in. All right, if you're just like, you know what, I'm fine, I'm good, I just know I'm going to add a multiple of 2 pi to get another solution. Or if you want to be fancy, one of the things to notice is that these solutions, pi over 6 and 7 pi over 6, are spaced pi units apart. So we can condense the first and the third statement into one statement, pi over 6 plus pi k. And then 5 pi over 6 plus pi k is taking the second and the fourth statements and melding them together. But you don't have to do that. If you're just like, I just know I get another solution when I add another 2 pi because I'm going around the circle another time, then you're good with that. All right, find all the general solutions to tangent sine of x plus square root of 3 plus tangent of x is equal to 0. That looks really complicated, but don't panic. Please don't panic. Because another step that you might try is to factor first. Notice that both terms in this equation on the left side have a tangent of x. So if I factor out a tangent of x, I get tangent of x times 2 sine of x plus square root of 3, all set equal to 0. Once you do that, set each factor equal to 0, and then isolate your trig function like we did before. So I set tangent of x is equal to 0, and I set 2 sine of x plus square root of 3 equal to 0. And if I solve for sine of x, I get sine of x is equal to negative root 3 over 2. And so now, in order to solve, we look at our unit circle. We notice that tangent is equal to 0 wherever y over x is 0, and that's at 0 and at pi. And then it's at 2 pi and 3 pi and so on. So we can write that one as x is equal to pi k. And then where sine of x is equal to negative root 3 over 2, I need to look at the bottom half of the unit circle, right? And that would be at 4 pi over 3, where y is equal to negative root 3 over 2, and at 5 pi over 3. And then, of course, to find our general solutions, we just need to add 2 pi k to each of those. Find all general solutions to sine squared x plus 5 sine of x plus 4 is equal to 0. This also looks really complicated, but in fact, it's not. If you remember back in the days when we solved exponential equations, one of our tricks was to substitute something to make this a simpler thing to work with. So notice I've got nothing but sine of x's, and one of them is squared. So if I make u equal to sine of x, I can rewrite this equation as u squared, that's sine squared of x, it's 5 times u plus 4 is equal to 0. And this is a nice, easy quadratic that we can actually solve here. So when I factor it, I get u plus 4 times u plus 1 is equal to 0. And then when I solve for u, setting each factor equal to 0, I get u equals negative 4 and u equals negative 1. But once you do that, you can bring the trig function back in, and you get sine of x is equal to negative 4 and sine of x is equal to negative 1. And so you use your unit circle to solve. Sine of x is never equal to negative 4, so there's no solution there. Sine of x is equal to negative 1 at 3 pi over 2 only, plus 2 pi k. And one of the things that you can do is on your graphing calculator or on Desmos or something similar to that, you can actually check to see whether this is actually true. And I did right here. So here's the graph of the left side of the equation, the sine squared x plus 5 sine of x plus 4. And where is this equal to 0? Well, it's equal to 0 at 3 pi over 2, and then 7 pi over 2, which is another 2 pi. Or we could go backwards 2 pi or backwards 4 pi, and we get solutions there. So it continues to give us a solution every 2 pi after 3 pi over 2. Find all solutions to 2 tangent squared plus secant squared of x minus 2 is equal to 0. So one more trick that we'll talk about is that identities are always helpful, and it's always helpful to try to get down to one trig function. In this case, we know that secant squared and that tangent squared are have a relationship with each other, and that's that tangent squared of x plus 1 is equal to secant squared of x. So in this equation, I can substitute secant squared x for tangent squared of x. And this all just becomes one equation in terms of tangent squared of x. So when I do that, I get 2 tangent squared of x plus tangent squared of x plus 1 minus 2 equals 0, which all reduces down to 3 tangent squared of x minus 1 is equal to 0. Now, again, we isolate our trig function. Tangent squared of x is equal to 1/3. And so tangent of x is plus or minus 1 over root 3. Or when you rationalize, you get plus or minus root 3 over 3. All right. Tangent is a function that actually has a period of pi. So in order to write our solutions, we know that tangent is equal to root 3 over 3 at pi over 6. And then every pi after that, because of the period of tangent, it's unique. And then tangent is equal to 5 pi over 6 or tangent of 5 pi over 6 is negative root 3 over 3. So we can add the pi k to that, and we get all of our sets of solutions here. All right, final example here. Final solutions for cosine of 2x minus pi over 2 is equal to root 2 over 2. Now this one also looks really complicated, but if you take it step by step, it's not bad. All you do is you determine normal general solutions to square root of 2 over 2 equal to cosine of x. So where's cosine equal to root 2 over 2? Well, that takes place at pi over 4 plus 2 pi k and 7 pi over 4 plus 2 pi k. If you go back and look at your unit circle, that's where x is equal to root 2 over 2. Then once you do that, all you got to do is set your new input equal to the normal solution. So our new input's not x anymore, it's 2x minus pi over 2. So I set 2x minus pi over 2 equal to pi over 4 plus 2 pi k, and 2x minus pi over 2 equal to 7 pi over 4 plus 2 pi k. Then we solve for x. So I add pi over 2 to both sides, and then I divide by 2. So I end up with x equals 3 pi over 8 plus pi k. So that divides everything by 2. And I get x is equal to 9 pi over 8 plus pi k when I solve the second set of equations. And this is verified by our trig graph here. This is cosine of 2x minus pi over 2. And it's equal to root 2 over 2 at pi over 8. And at 3 pi over 8, 9 pi over 8, 11 pi over 8. So it repeats. All right. I want you to notice also this cosine graph is happening twice as fast as the normal graph. That's why we get solutions that happen every pi, not every 2 pi, right? Because our solutions are happening twice as fast. So in summary, algebra comes into play when we try to solve a trigonometric equation. We're trying to figure out what x values actually work in this case. And you may either be asked to find all solutions or, on a particular interval, so 0 to 2 pi typically, or to find general solutions. That's where that 2 pi k comes in. Thanks for listening. We'll see you on the next video.